Hello students, I am Dr. Navneet Kaur, Associate Professor in Department of Electronics and Communication, Sagar Institute of Research and Technology College, Bhopal. Today I'll be taking lecture on subject digital communication. The topic which I'll be discussing in this lecture is quadrature phase shift keying receiver. This is the block diagram of quadrature phase shift keying Qpsk receiver. In my previous lecture, I had discussed about Qpsk transmitter, in which we have done how we have generated Qpsk signal. When the Qpsk signal is generated at the transmitter side and the signal is transmitted across the channel, it is received at the receiver side. Say the signal is ST. Now, in the transmitter section, we have already done that the two types of carriers are used, which are at phase difference of 90 degrees with each other, which is cos omega naught t and sin omega naught t. In Qpsk receiver, the demodulation method used is synchronous detection method. In synchronous detection method, the synchronized carrier, which is used at the transmitter side, is generated at the receiver. Since we have used cos omega naught t and sin omega naught t at the transmitter side, so here we will generate synchronized carriers at the receiver. And for that, we will use the carrier recovery circuit. In carrier recovery circuit, we have three components. First, we will take the received signal and raise the input to fourth power. So we will get s raised to power 4t. Then this signal will be given to the band pass filter. This band pass filter will operate at cutoff frequency 4f0. That means it will select the signals which are at 4f0 and it will reject all other signals. So here we will get cos 4 2 pi f0 t or sin 4 2 pi f0 t signals, and all other signals which are at some other frequencies will be rejected. Then this signal will be given to frequency divider circuit, which will divide the frequency of the signal by 4. So here we will get two signals, which will be cos 2 pi f0 t and sin 2 pi f0 t. Here we can see the frequency of the input signal is divided by 4. So now we have generated synchronized carriers cos 2 pi f0 t and sin 2 pi f0 t. Now we will use the multiplier circuit and we will multiply these synchronized carriers with the incoming received signal. So here we will get st into sin 2 pi f0 t and st into cos 2 pi f0 t. Now these two inputs will be given to the integrator and dump receiver. Integrator circuit will sum up the input for 2-bit periods. Why 2-bit periods? Because we have already done that in Qpsk, each symbol, it consists of 2 bits. So here at integrator and dump receiver, each integrator will integrate the input for 2-bit periods. Now the upper integrate will integrate for odd bits, so it is 2k minus 1 dB to 2k plus 1 dB. Whereas the lower integrate will sum up the incoming signal for 2-bit periods, which is 2k dB and 2k plus 2 dB. Now the output generated will be BET TB into root PS and B0 T TB into root PS. This output derivation we'll be discussing in our successive slides. Now these two outputs will be given to the multiplexer circuit, which will take these two signals alternately. Now here TB is the bit period which is having a fixed value. PS is the power of the signal, which is again having a fixed value. So here the value which changes, which represents the signal, is BET and B0 T. B0 T means odd number of bits and BET even number of bits. So here this multiplex will take B naught T and BET alternately. That means odd bits will be taken from lower input and even number of bits will be taken from upper input, and alternately even and odd bits will be combined, and they will be combined in the form of 2 bits and will be generated at the destination end. So this I have already discussed, synchronous detection method, then integrator circuit also. Then at the end of the period, I have already discussed the output of the integrator is sampled and the output of the multiplexer will be the signal BT, where odd and even sequences are combined by multiplexer. Now, coming to the output of the integrator and dump receiver. Now here, we have already taken the output ST into sine 2 pi f naught t, which will be generated by multiplying the received signal with the synchronized carrier. Now, ST, substituting the value of ST here, B naught t root PS cos 2 pi f naught t plus BET root PS sine 2 pi f naught t. So here, when I'll multiply ST with sine 2 pi f naught t, the resultant signal will be like this. Now, this signal will be given to the integrator, which will integrate the incoming signal for 2-bit periods, 2K minus 1 TB to 2K plus 1 TB. Now, using the integration property, the integration of the sum is same as the sum of the integration. So, we will separate the integrator for 2 functions. So, using the trigonometric functions, sin x cos x can be written as half sin 2x, and sine square x can be written as half 1 minus cos 2x. So substituting these trigonometric values here, we will get sine 4 pi f naught t. The common terms are taken and the constant terms are taken outside the integrator sign. So here we have B naught root PS upon 2 sine 4 pi f naught t, BET root PS upon 2 1 dt, and minus BET root PS upon 2 cos 4 pi f naught t. Now, the first and the third integration term, it involves integration of the sinusoidal carriers over 2-bit periods. And we have integer number of cycles of carrier signal for 1-bit period. So there will be integer number of cycles for 2-bit periods also. So whatever the number of positive values will cancel with the negative values of the carrier signal. So hence the integration will be 0. So here the first and third integration will be 0 and we will evaluate only the second integration. So the integration of 1 is t. When I integrate between these 2-bit periods, these 2 values, I'll get BET root PS TB. So this is the output of the upper integrator. Similarly, when I'll evaluate for lower integrator, I'll get B naught T root PS into TB. Now, signal space representation of the Qpsk signal. Now, in general form, the Qpsk signal can be represented as root PS cos 2 pi f naught t plus 2m plus 1 pi by 4, where m is having 4 values, because here we are having 4 symbols. So m is equal to 0, 1, 2, and 3. When m is equal to 0, we will get the first symbol. 1, when m is equal to 1, second symbol, 2 will give the third symbol, and 3 will give the fourth symbol. Now, using the trigonometric function, root PS cos 2 pi f naught t cos 2m plus 1 pi by 4 minus root 2 PS sin 2 pi f naught t sin 2m plus 1 pi by 4. Now, we will take 2 orthonormal carrier signals phi 1t and phi 2t. Phi 1t we will substitute by root 2 upon ts cos 2 pi f naught t, and phi 2t is root 2 upon ts sin 2 pi f naught t. Now substituting phi 1t and phi 2t here in this expression. Now we have done one more substitution. Root 2 cos 2m plus 1 pi by 4 is say b naught t, and minus root 2 sin 2m plus 1 pi by 4 is bet. If we will solve this function for values of m is equal to 0, 1, 2, and 3, we will always get either 1 or -1. Same is the case for B0T and BET. B0T and BET are having values either 1 or -1. Now substituting these values, we will get this expression. Now by solving it again, we can get root PS TS by 2 B0T 5-1T root PS TS upon 2 BET 5-2T. Now we already know that each symbol consists of 2 bits. So substituting TS is equal to 2TB here, 2 and 2 will get cancelled and we will get root PS TB in both the expressions. So root PS TB, we already know it is given by bit energy EB. So it will be root EB B0T 5-1T plus root EB BET 5-2T. Now we will represent it in the signal space. Say this is 5-1T and this is 5-2T. Since 5-1T it constitutes cos omega naught T and 5-2T it constitutes sin omega naught T, there will be a phase difference of 90 degrees between these two orthonormal signals. Now when BET is equal to -1 and B0T is equal to +1, that means the second term is negative and the first term is positive. In that case, we will take the negative direction of 5-2T, which is in the upward direction, and we will take positive direction of 5-1T, which is on the left hand side. So this is -5-1T and this is +5-1T and this is -5-2T. Now I'll take the resultant because these are two vectors 5-1T and 5-2T. Now according to the parallelogram law of addition of vectors, the resultant will be given by the length of the diagonal of this parallelogram. So the signal point will be represented by point B, which is at the distance from the origin OB. Now this signal will represent BET is equal to -1 and B0T is equal to 1. Similarly, if I'll take BET and B0T both as -1, that means I'll take the negative direction of 5-1T and 5-2T. So in that case, -5-1T and -5-2T, it will be represented by signal point C. Again, it will be then D, and for another symbol, it will be A. So here we can see that there is a phase difference of 90 degrees between two symbols. Now, if I want to find out the distance of the signal point from origin, now using the Pythagoras theorem, this distance, Pythagoras theorem is hypotenuse is given by under root of perpendicular square plus base square. So we will here root EB here, root EB here. So according to the Pythagoras theorem, it will be root EB plus square root EB plus EB, which will be 2 root EB, 2 EB, and it will be given as root ES. So here the distance of the signal point from origin OB will be root ES. Now, if I'll find out D square, which is the distance between two signal points. Distance between signal points means if I want to find out the distance between AB, BC, CD or DA. Now, if I want to find out the distance between the two signal points, it will be represented by, say, D. It will be root 2ES. So D is equal to twice root PSTB, which will be twice root EB. Here we can see that the distance between the two signal points in Qpsk is same as that we calculated in BPSK. So the noise immunities in both the cases, BPSK and Qpsk, is same. Now this is all for today's lecture. Thank you.